we now have a whole bunch of ways of solving equations. What equations? All of the things we were doing back at the beginning of chapter 1, where we started talking about what does a differential equation represent, can now be solved. So we can sit down and pick any of the situations we had set up. Growth and decay. This was a model that looked like this. And then K tells me whether I'm growing or decaying based on the setup. So here, let's suppose I have a population at time 0, it's 500 people. And P is increasing by 15% in 10 years. Increased by 15% 10 years. I would like to be able to come up with a formula for the population at any given time. There are two pieces of information given to me here. The population at time 0 and the population 10 years down the line. But that's all I know at this point. And if that's all I know, I'm not sure I have enough information to solve for K right away. So let's actually solve this differential equation without any numbers in it. And then we'll go through and figure out what the numbers are. We did this. How do I solve this differential equation right here? K is a constant. Is it exact? Is it linear? Is it separable? How do you want to do this? It's separable. So how am I going to do it by separating? Okay. And now? On the left, I get and on the right, so I go to get rid of the ln and I do what? And now is where a sneaky trick comes into play that we talked about. What can I do with that KT plus C? Multiply the and that's just another constant. Now, I'm going to keep this because any equation that looks like that is going to have a solution that looks like this. So I already know my P of t has got to look like this. The question is, how do I find A and K? Okay. If I plug in 0 and 500, what does that give me? A, because either the 0 is 1. Oh, so A is 500. How do I get K? How? What's that equal to? No, don't give me a number. What's the other side of the equation here? Hey, if I divide out the 500, I get 1.15 is e to the 10k. If I want to get rid of an e, I can do the reverse of what we did over here, solving it. I can take the natural logarithm. 10k is ln of 1.15. So k is 1/10 ln 1.15. And now I know the equation for the population at any given time. My population at 30, at 70 years, at 235 years, I can find out. Questions? If you want, you can give me a decimal here. I don't know what that decimal is, but I do know that decimal is positive. Why do I know that? And e to the something t looks like this when that something is positive. It's increasing as we go from left to right. If we use a negative number for an exponent, then it'll be decreasing as we go from left to right. So I can automatically do some checking here. As soon as I get that value for k, does that match the sign of the thing I want to know about? I'm a geek. I used to be a physics geek. Radioactive decay, anybody? Thorium-232 has a half-life of 1.4 times 10 to the 10th years. 14 billion years radioactive thorium hangs around. But when it decays into radium-228. Radium then decays into actinium, which only has a half-life of 6.25 hours. Radium-224 has a half-life of 3.66 days. But you see, eventually we end up at lead-208. Lead-208 is stable. Once you hit lead-208, you're done. But you can also look at uranium decay. Uranium decays into thorium. Thorium-228. protactinium to a different variation of uranium, and so on and so on, and eventually becomes lead stable. But there are multiple versions of lead, as we see here: lead 214, lead 210, lead 206. The difference in atomic weight is because they contain extra neutrons and thus emit beta particles to shed those other elements. Those beta particles are the radiation. Lead 214 has a half-life of less than half an hour. When you encounter lead 214, it decays very quickly into bismuth, which then unfortunately emits polonium, which is poisonous. But please notice the half-life of polonium is measured in milliseconds. So there isn't very much polonium for very long. I think I gave you this example when we talked about the models of me getting this cardiac stress test with the technetium-99. This is the same sort of crap, but this is the bomb. U-238, that's the uranium bomb, that's the nuclear weapon. This is the decay chart for the radiation after a nuclear explosion. I'd love to tell you this is useless crap. This is this model. Only the number K is a negative number. Problem number 5 out of the textbook talks about lead 209. Oop. I knocked my camera off. That doesn't help. Lead 209 decaying with a half-life of 3.5 hours. If you start with a gram, how long until it's down to 1/10 of a gram? But you can go through that. If I tell you a safe exposure is 1%, how long does it take to get there? I can't go to the airport for two days after my stress test because I look like a bomb to the radiation detectors. It doesn't have to be radiation. Intensity of light underwater. As you go down under the surface of the water, light has harder time getting through the water. So if I shine a beam of light straight down into the water, the intensity of the light is directly proportional to the thickness of the medium. So the thickness of water above me tells me how well light can penetrate. Well, that means the change is proportional to how deep I am. The change in the intensity of the light, well, I'm not sure I should use T here. I want to use distance. I'd be using D. That's a bad idea. Let's use T anyway. But T here represents depth, not time. Is proportional to my depth. Sorry, the intensity left, not right? No, that's right. I've written it down, and I say to myself, no, it isn't. It's proportional to I of T. That's an I, not a T. I can read my own handwriting, I promise. Sorry. Oh, wait a minute. That looks just like our population equation, doesn't it? If I tell you that in this particular lake that I am swimming in, I start at the surface with my light meter, and I notice it's reading. I don't know what the units mean. I don't know what the appropriate lumens measurement is here, but it tells me how bright the light is right at the surface of the water. I go down 3 feet, and I notice that only a quarter of the same light is getting through. What happens if I go down 15 feet? Can I see anything? Now, here's the worst part. The worst thing you could do here is you say, oh, well, I went from here to here and I cut my by 3/4, right? So I should cut it by another 3/4. That would give me -1/2. How do you have negative light? That don't make any sense, right? I know the equation for I must look like that. It's the same model. It must have the same solution. But now I'm in the same place, Divine. How do I find A? How do I find K? Man, we do the same stuff, right? I have two pieces of data. I have two variables I don't know. Plug them in, find out what we got. I of 0 is A e to the K times 0. That's just A. So A must be the initial amount of light. And that means that my equation really looks like I of t equals I0 e to the kt. Give me k. Talk to me. No? You're gesturing at me or just gesturing? I used this condition to find one of them. Let's use the other condition. So I of 3 is 1/4 I0. That's I0 e to the k times 3. Hey, the I0s are going to cancel from each side, right? So I get 1/4 is e to the 3k. Now what? I take the logarithm to get rid of the e. So really there's a step in between here that says ln of 1/4 is 3k. And then I divide by 3. I hate taking the logarithms of fractions. I would rather change that to subtraction sort of deal, but you don't have to. That's a negative number. ln of 1/4 is like -1.38. Then I'm dividing by 3. It's still a negative thing, right? That's all I need. This is decaying. What is my visibility at 15 feet? So now, what is I of 15? there will be an I0 in your answer. I'm really looking for the number next to the I0.
1/3, ln 1/4, multiplied by 15.
Yeah. I of 15 is I0 e to the 1/3 ln 1/4 times 15. So what is this number? Give me at least, I don't know, 4 or 5 decimal places. All right, wait a minute. That is less than 0.1% of the light that was visible at the surface. All I had to do was go down 15 feet and it's 99.9% dark. Lights went out all over the world. This is why submarines and submersibles have huge, dramatically powerful spotlights, because we can't see squat down there. Now, I'm pretty sure 3 feet is the wrong unit. Maybe 30 feet would get me to a quarter of the visibility. Well, so just put an extra 0 on all the feet number. 30 versus 150. I don't care what problem setting we're looking at. What were some of the other problem settings we were looking at back in chapter 1? By the way, one of my favorite examples is in this text about carbon dating. What's carbon dating? Anybody know? How? What's the carbon part of dating that? Okay, carbon comes in 2 varieties, carbon 12 and carbon 14. Carbon 14 is radioactive and sheds those 2 neutrons in a beta particle to go to carbon 12. So if you measure the carbon 14 amount today versus the carbon 14 amount in something that's dead, the carbon isn't being maintained and renewed, right? So I can tell how old something is by looking at the proportion, right, of carbon 14 in it. These are about the cave paintings in France. Tell me how old the cave painting is by looking at the burned wood that they used as charcoal to make the cave painting. That's dead wood. Its carbon isn't being renewed. I compare it to live wood today and measure the ratio of carbon. I show that that painting is 80,000 years old. Temperature, electricity, mixing stuff, all of the scenarios we looked at are now solvable with methods we know. Problem 21, a dead body in a closed room. A dead body was found in a closed room where the AC was set at 70 degrees. The body temperature is 85 degrees. An hour later, the body temperature is 80 degrees. How long has this person been dead? From the time we find the body, let's call this one time 0. How long before time 0 did this person die? All right, wait a minute. The setup for cooling was the temperature changes proportional to the difference of the temperature and the temperature of the surroundings. That's what TS is. the surrounding temperature. So in our case, what's TS? The 70 degrees. So I think about this like that. I claim this is still the same model. How do you know I'm not blowing smoke up your ear? If I make the substitution, what's dy dt? We did substitutions for a reason. What's the substitution here? Sorry, what's the differential for this substitution? Exactly, it'd be d capital T dt. Minus 0, because 70 is a constant, right? Which makes this expression dy dt equals ky. It's the same flippin' model. That means that the solution looks like y equals a e to the k t. But y is t minus 70. Or t is 70 plus a e to the kt. Now, how do I find a and k? Unfortunately, the information is no longer on the screen. How do I find a and k? There. So I have 85 equals 70 plus a e to the k 0, because that was what we said was time 0. What's e to the 0? So this is just 70 plus a, which means a is, that was nice and easy. Now I can use the other one to solve for k. Now you have to make an executive decision here. What units are you using for time? That is not an idle question. I need to know what your units are so I can interpret the answer in the units you give me. How do you want to measure time?
Hours.
Hours? Okay. And it said 1 hour later, right? So T equals 1 hour. The temperature was 80 degrees. So now 80 equals 70 plus 15 e to the k times 1. And I can solve for k. Subtract the 70. 10 equals 15 e to the k. Divide 2/3 equals e to the k. Take the logarithm. K is ln of 2/3. That is a negative number. Why does that make sense? I should be losing temperature, right? I'm not producing any heat anymore in this dead body, right? It's not spontaneous combustion. How do I figure out when the person died?
Total time, the body gets like a certain temperature. Or like, they go for whatever.
Well, we know they're getting colder, right?
We know their temp's supposed to be like 98.6 degrees. Yeah.
When they're alive, so I can work backwards in time, right? So I can say, oh, at what T was the temperature 98.6? Now, it turns out, just for the record, that 98.6 is actually a really bad guess at what the human body temperature is, because for the past 20-ish years, human body temperature has on average gone down. The average temperature is much closer to 97.9 or 97.8 than it is 98.6 now. No idea why. I'm not in charge of any of the knowledge of medicine. I just know what the statistics tell me. Average body temperature is going down. Oh, but now I can take the model we already have, plug in 98.6, and solve for the time. So I get 28.6 equals 15 e to the, wait a minute, e to the ln 2/3, e to the ln, e to the ln, what happens? Say that again, though?
They like cancel out.
Yeah, but what do I do with the t then? Because, it only drops down if we were dropping it down in front of the ln, right? But it's already being multiplied, isn't it? This is really the same as e to the t times ln of 2/3. I just put the numbers in the other order, right? Let's not drop it down, Noah. Let's go backwards. Where does it go? Where's that t go? Unfortunately, no, it doesn't go to the 15 unless I'm taking a derivative. I'm not doing any derivatives here. It becomes an exponent. So that's going to be 15 e to the ln 2/3 to the t power. Now when they cancel out, it's 2/3 to the t. You will often see any equation where I've got a logarithm for the constant rearranged like this. I needed you to see that. I'm not sure it helps us in the solving, but it certainly does help us here. What's the other side of this? The other side of this is 28.6. I divide to get rid of the 15. 28.6 over 15 equals 2/3 to the t power. I got to take a logarithm anyway, don't I? To get rid of the power. So I end up with t is the log base 2/3, 28.6 over 15, which is the same as ln of 28.6 over 15 over the ln of 2/3. Change of base formula. What is this t value? Calculator time. So negative 1.59 hours. If time zero is when we found the body, we're looking at a negative time when he was last alive. He's been dead for an hour, 0.6. What's 0.6? 36 minutes. 96 minutes ago, something caused this man to die. Not even 2 hours.
That time, like the time before, like he was dead an hour, 1.6 hours before they found it.
Right. Because we said that time zero was when we took the temperature. So having this be a negative means it was before we took the temperature. If I know what time that is, I can work backwards, tell you how long this person's been dead an hour and a half. Little over. We did mixing problems, right? We had the tank with the salt going in and out, right? Problem 25. A large tank is filled with 500 gallons of water. Brine containing 2 pounds of salt per gallon is pumped in at 5 gallons a minute. Then it's mixed and pumped out at the same rate. How much salt is in the tank at any given time? Salt in minus salt out, right? Problem number 25. I think of my salt tank. Salt tank, 500 gallons. Salt goes in, 2 pounds per gallon, 5 gallons per minute. Stuff comes out at 5 gallons per minute. And I'm going to let A of T represent amount of salt in the tank at time T. I was given 2 other pieces of information in the problem. I was told that the solution that is coming out is well mixed. And I was told that when I start, what do I know about the tank? When I start, what do I know about the tank? Of, which means how much salt is in the tank? At time zero, 0 salt. I have an initial condition. A of 0 is 0. But you'll notice I'm missing something in the difference between the 2 arrows. Over on the left, you can tell me how much salt is going into the tank. How many pounds of salt go into the tank every minute? Into the tank. Oh, I got different numbers here. Wait a minute. Why 10, Hayden?
5 gallons a minute and then 2 pounds per gallon.
Cancel my units and I get pounds per minute. Right. So I got 10 going in. So salt in equals 10 pounds per minute. But salt out doesn't look like that. What's missing for salt out? The amount of pounds, right? But that's because the salt out depends on how many pounds are in the tank. But what are the units for salt and pounds over there on the left? On the top there, it's pounds per gallon. I have gallons per minute. I have gallon minutes. I wrote the wrong unit. Gallons per minute. Good Lord. Gallons per minute. I need pounds per gallon. How many pounds per gallon is in the stuff coming out of the tank? Well, it's however much salt is in the tank divided by the size of the tank, right? Pounds per gallon here is A over 500. The amount of salt in the tank divided by the amount of gallons in the tank. Which means salt out is pounds per gallon times gallons per minute gives me pounds per minute. Change in salt is salt in minus salt out. This one's not separable, but it is solvable. What's the setup here? Because if I move the A over 100 to the other side, there's P of T. This is solvable. And that means my integrating factor is e to the integral of minus 1 over 100 dt, or e to the minus 1 over 100 t. Oh, you're right. I moved it over. It's positive. Good catch. Move it over. It's positive. 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 Thank you. That's good. That would cause me a big problem later. So I get e to the 1 over 100 t dA dt plus 1 over 100 e to the 1 over 100 t a equals 10 e to the 1 over 100 t. The left side's a product rule. It is e to the 1 over 100 t times a when I integrate the thing on the right. What do we get on the right when we do that integral? Right, because it's 1 over 100 times the 10 plus c. But wait a minute, that's equal to e to the 1 over 100 t a. Here's why I'm very happy, Divine, that you pointed out the sign error to me, because I'm going to divide And when I divide, that'll change that power to be negative, won't it? So A is 1,000 plus C e to the minus 1 over 100 t. I'm happy to see that power be negative because that makes that a transient solution. It goes away in the long run. What is the limit as t goes off to infinity of this expression? As t gets bigger, what happens to e to the negative t? It gets small, which means eventually this piece is 0. In the long run, I will have 1,000 pounds of salt in the tank. Wait a minute, how big was the tank? And how dense was the salt we were putting in? 2 pounds per gallon. Shouldn't we eventually have 2 pounds per gallon times 500 gallons? 1,000 pounds of salt. By the way, we can figure out C. How do I figure out C? I started with an initial condition. At time 0, we had no salt. A of 0 equals 0. Solve for C. By the way, problem 27 wants you to rework this. It says in this same tank, what if you were pumping out twice as much as you were putting in? So you're taking salt out at twice the rate it's going in. It was going in at 5 gallons a minute. Now you're taking it out at 10. What's eventually going to happen? You're putting liquid in at 5, you're pulling it out at 10. What eventually happens? You run out of liquid. The tank will eventually go dry. So now there are 2 questions. When does it go dry? And how salty was the water when you pulled it out at the very end? Both of those are answerable questions. But what changes is here. Because this is no longer 500 all the way through. At different times, we have less water, right? Every minute that goes by causes us to lose 5 gallons. Putting in 5, taking out 10. So this bottom changes and now becomes 500 minus 5t. For every minute that goes by, I lose 5 gallons. Changes that right there. And then we get a very different problem. I talked about throwing myself out of an airplane. Here's our terminal velocity question. What happens if I change my drag coefficient? There'll be 2 different initial values. There'll be the initial value while I don't have the chute open, and then I open the chute. What changes? That's a homework problem. There are dozens of different scenarios where the same type of equation, now that we have the solution techniques, becomes tractable. All of the types of equations we were doing are first order, linear, separable, or exact. These were all linear models. What happens with nonlinear models? That's next. I will see you all then. Have a wonderful rest of your day.